So in the previous class, we have derived the relationship between unit step and unit impulse signal. Okay, so particularly in the continuous cases, it's very important for your exam point of view. Okay, so from the relationship, we can write integration minus infinite to t del of tau d tau equal to u of t. Because if we integrate this signal from minus infinite to t, for t less than 0, no information available. You will get 0. If t is greater than 0, you will get 1. Okay. So this is similar to your unit step signal property. U of t equal to 1 for t is greater than 0, 0 for t less than 0. So we can write it as integration of del of tau d tau equal to u of t. Okay. From minus infinite to t. And now we need to write u of t in terms of del functions, or del of t in terms of u functions. Okay. For that, we have taken u of t signal initially, and we have made some assumption. Assume there is a slope. Okay, the width of the slope is del. There is u del of t. If del approaches 0, then this u del of t is equal to your u of t signal. Right? Now differentiate this particular signal. If we do the differentiation of this particular signal, wherever the constant line is there, you will get 0. Okay. For this slope, if you do the differentiation, and 1, this height is 1 by del. So you will get the rectangular pulse corresponding to this particular slope with the magnitude of 1 by del, the slope of this. Okay. Here it is constant from del onwards constant. So differentiation with respect to constant, you will get 0. Okay. Now in this rectangular pulse, the area under this rectangular pulse is 1, because 1 by delta height and delta width, if you multiply 1. Okay. With some approximation, we are going to get unit impulse signal from this a small rectangular pulse. Okay. So we need to maintain the area under this rectangular pulse is 1, and reduce this pulse width towards 0. If you reduce this pulse width towards 0, then we need to increase the height of the pulse to maintain the area under this pulse is 1. Okay. Assume your pulse width is 0. So 1 by 0, you will get infinite. So the impulse signal derived from this a small rectangular pulse having the width of del and having the height of 1 by del initial. Okay. With some assumption, we can represent the impulse signal like this. Now width is 0. The height is infinite. This arrow mark indicates the height of this pulse is infinite. This 1 indicate the magnitude, the area under this curve is 1. Okay. So d by dt of u del of t in this signal, if del approaches 0, this is equal to your del of t. Okay. So this is the relationship. So differentiation of u of t equal to del of t. Integration of del of t is your ut. So we have summarized finally. Integration over minus infinite to t, you'll get ut. Okay. Or u of t, if you differentiate with some approximation, you will get del of t. So this relationship is very important for theory point of view. In today's class, a few properties of unit impulse signal, and then we'll start classifications of systems. Right. So before discussing about properties of unit impulse, let me recall the impulse function, unit impulse function. Del of t equal to 1 for t equal to 0. Del of t equal to 0 for t is not equal to 0. So this is a graphical representation of unit symbol. When t equal to 0, the magnitude 1. For continuous time impulse signal, you have to mention this arrow mark. Okay. And also the integration from minus infinite to infinite. If you integrate the signal from minus infinite to infinite, the del of t, your result will be 1. Okay. So this is the unit impulse signal. So what are the properties of this unit impulse signal? First property, integration over minus infinite to infinite. If we multiply any signal x of t with del of t, okay, x of t del of t dt, then you will get the result of x of 0. Hmm? How it happens? Let's say, for example, this is a signal x of t. Okay. Now multiply this signal with del of t. What is the signal sketch for del of t? Del of t at t equal to 0, the magnitude of the signal is 1. Multiply these two signal and then do the integration. If you multiply these two signal, what will happen? Here everything is 0. Here also everything is 0. Okay. So at t equal to 0, 1. At t equal to 0, let us assume this is some value of 2 something. Let assume the magnitude is 2. Okay. Now the resultant for this integration, because minus infinite to infinite, you cannot do the integration because del of t is valid when t equal to 0. At that particular time instant only the del of t is valid. Remaining all other time interval, this product will be 0. So this integration of x of t del of t dt, the result is what is the magnitude at x of 0? At t equal to 0, what is the magnitude in x of t? So that is your result. You multiply these two signal, 0, 0 and everything 0. Here also 0 multiplied by everything 0. At exactly t equal to 0 only, it has the values. At that time only the product is valid. X of t into del of t. So the integration of any signal multiplication with a del function, the result is simple. Whatever the magnitude available at t equal to 0, that is the result. This is property number 1. Second property, suppose if you multiply a signal with shifted version of the impulse signal. Shifted version of the impulse signal. Now what would be the result? You can tell me, you can answer easily. Because from the previous example, when you multiply x of t with del t, your result would be x of 0 only. Okay. Now if you multiply x of t dot del of t minus t naught, this t naught may be anything, t minus 2 or t plus 2, whatever it may be. Say for example, I'm consider the same x of t. Now multiply that x of t signal with del of t minus 2. Del of t minus 2 meaning at t equal to 2, the magnitude is 1. This is del of t minus 2 signal. Okay. Now if you multiply x of t del of t minus 2, at t equal to 2, what is the information, the magnitude? What is the magnitude of x of t? So this is x of t minus 2. At x of t minus 2 position, what is the value? Okay. Or x of t naught, sorry. X of t naught. X of. So del of t minus t naught. Let assume t naught is 2. Then the impulse signal sketch is like this. So now if you multiply this x of t with del of t minus 2, your result is valid at exactly t equal to 2 only. Okay. So 1 multiplied with at t equal to 2, what is the magnitude that you will get? So you can write it as x of t naught. Shifted version of impulse signal multiplied with any signal x of t. And even if you do the integration also, the result would be equal to x of t naught. At t naught, what is the magnitude present? That is your result. Okay. Property number 3. Integration minus infinite to infinite. X of t del of t minus t naught equal to x of t naught. Okay. It's repetition. Okay, fine. Or you can express the same thing, x of t del of t minus t naught dt. This will be equal to x of t naught into del of t minus t naught. Okay. Because these two multiplication valid exactly at t equal to t naught. Both are same. Right. Because by default this value will become 1 at t equal to t naught. Then you will get this relationship x of t naught. So property number 4, not giving any proof for this. Just remember del of at, because we studied time scaling properties of signals, all basic signals. Okay, some kind of x of t signal given, we performed many operations on that signal, like time shifting, time reversal, time scaling, magnitude shifting, magnitude scaling, addition, subtraction, etc. So now del of at, because del function has the value at t equal to 0 exactly. In remaining values of t, it is 0. That is del function. Okay. At t equal to 0 only, the magnitude is 1. Impulse function. So del of at, the answer would be 1 divided by modulus a into del of t. Please remember this property. Del of at equal to 1 by modulus a del of t. So there will be proof for this. I'm not solving this proof and not required also. Just remember, if there is problem involving in del of at, then we have to use this particular formula one. Okay. The last one, x of tau del of t minus tau. So this is convolution property. We will discuss in unit 2. X of tau del of t minus tau into dt. The value is x of t. Okay. So this we will discuss in unit 2. That is a convolution between a signal with a del function. Your result will be equal to x of t only. Convolution properties of impulse signal. What do you mean by convolution property? That we will discuss in unit 2. So these are some of the basic properties of unit impulse signals. Now we will solve some problems based on the integration and the integration function involving the del functions. Evaluate the following integrals. Evaluate the following integrals. First example, minus infinite to infinite e power minus alpha t square into del of t minus 10 into dt. Okay. So how to solve this kind of integration? In the integration, if del functions are involving, then how to do this? What do you mean by del of t minus 10? How to sketch del of t minus 10? At t equal to 10, the magnitude is 1, correct? Del of t signal delayed by 10 unit of time, or del of t signal shifted right side by 10 unit of time. So e power minus alpha t square multiplication with del of t minus 10. This product is non-zero value. This product is valid when at t equal to 10, correct? At t equal to 10, this particular term will be 1. So 1 dot e power minus alpha t square. Exactly t equal to 1 only these two products are valid. Remaining all other time interval del of t minus 10 is 0. So 0 multiplied with anything 0. So the answer for this integration, wherever the del function is involving, you have to check del of 0. At what value of this t, you will get del of 0. Okay. When t equal to 10, you will get del of 0. That is the magnitude is 1. At t equal to 10, the magnitude is. Okay. So the result is in the rest of the term, whatever term available in the rest of the places, you have to rewrite the same term by replacing this t by same value, 10 square, e power minus 100 alpha, okay? E power minus 100 alpha. So this is the result for this integration. You cannot do the integration by substituting the lower limit, upper limit, because the impulse signal valid at that particular time instant only. So how to solve the integration if the impulse function involving, we have to check when the del of function would become 1, or at what values of this small t this del function value 1. Then write the result remaining all the terms available in the expressions by replacing the small t by this value. In this example, del of t minus 10. So del of t minus 10 equal to 1 for t equal to 10 only. So in the rest of the equation, wherever the small t variable is there, those t replaced by this 10. That is your result. This way only we have to solve the integration if the impulse function is involved. So one more example I'll give you. Evaluate the integration 0 to infinite t square del of t minus 3 into dt. Second example. So like this, many problems are there in signals and system by Ramesh Babu reference books. You can refer those problems. Evaluate the following integrals. Now tell me t square dot del of t minus 3. So when this product is valid, del of t minus 3. Del of t minus 3. When it become 1. What is the sketch for del of t minus 3? At t equal to 3, the magnitude of the impulse signal is 1. Okay. Or otherwise, this del of t minus 3 equal to 1 at t equal to 3. 0 otherwise. Right? So now if we multiply t square dot del of t minus 3, this value is 1 at t equal to 3. Remaining all other values of t, it has 0. So 0 multiplied this value is 0. So the result of this integration, this is 1 t square. So del of t minus 3 equal to 1 or t equal to 3. So this t is replaced by this. The result is 9. Okay. So one problem I'll solve. Remaining problem we can do. Suppose minus infinite to infinite, e power minus j omega t or e power minus j3t dot del of t dt. So what is the result? Integration minus infinite to infinite, e power minus j3t del of t dt. Del function. What is the sketch, signal sketch for del function? At t equal to 0, the magnitude under this curve is 1. That means the del of t is valid exactly t equal to 0 only. Remaining all other time instant, the magnitude of the signal is 0. So this particular information equal to 1 for t equal to 0 only. So the result is rest of the term e power minus j3. This t also replaced by 0. That is your result. E power 0 values. Okay. So this is some basic idea. So from this, I hope you can solve any kind of given integrations. Okay. So with this, we have completed the signals part of unit 1. When compared with the system part of unit 1, signals part is very huge topics, very huge syllabus. Okay. So quickly we will recall whatever the topics we covered. Classifications of signal. You may expect the theory questions. What are the different classifications of signals and explain with suitable example. Okay, don't say we concentrated only problems for the examinations and all. Okay, then you have to write down clearly. And signal classification and basic operations on signal, both continuous as well as discrete time signal, we solve many problems. Okay. And the classifications of signals, particularly the periodic and aperiodic. You may expect the problem from periodic and aperiodic, energy and power signal, even signal and odd signal. Okay. Out of the 6 classifications, remaining the three are very simple. Causal, non-causal, you can identify easily. If any information exists negative value of t, then it is non-causal. Okay. This is just definition only, deterministic random. Even signal, odd signal, either in the form of sketch or the mathematical expressions. And periodic and aperiodic signal. Identify periodic or aperiodic and how to find out the fundamental time period. And how to identify whether the given signal is energy signal, power signal. These 3 cases, both continuous time signal as well as discrete time signal. Okay. Then some theory questions available, that is relationship between a unit step function and unit impulse function. Then you have to explain neatly with the sketch and the necessary equations. And finally, you prove it. Okay. And these properties of impulse. Sometimes if they are asking in the examination, then you have to list out the properties. And how to evaluate the integration if the impulse function is involved. Because the impulse function mostly we are using as a test purpose only to test the systems. Okay. It is available exactly at that particular time instant only. So you cannot integrate because integration from a particular point to the some other point, lower limit, upper limit. You cannot substitute this lower limit and upper limit for impulse related functions. Okay. You have to solve the impulse related integration by checking when the del function would become 1. At what value of t the del function would become 1. Then you have to replace the small t in the rest of the places in the given equations and write down your result. And today class we will start the classifications of system. What do you mean by system and classifications of systems? I think before that, suppose this impulse function given in the form of summation. For this problem, you have to answer for me now. N equal to minus infinite to infinite, e power 2n del of n minus 2. What is the result? Everyone listening in the classes? Shall I call the roll number wise? summation minus infinite to infinite e power 2n del of n minus 2. What is the result? What is the result?
Then n minus 2 will be shifted to right.
Anybody else? I think some disturbances. I could not able to hear properly from her. Any other students? What is the result? What is del of n minus 2? It's a discrete time impulse function. At n equal to 2, the magnitude of this del of n minus 2 is 1. So now this product is valid at n equal to 2 only. Remaining all other time instant, this product is 0. Okay. So now the result of this summation e power 2 at what value of n this del function would become 1. That is n equal to 2 e power. Okay. So evaluate the integration. That is continuous time impulse function involving. Or evaluate the following summations. This is an example for discrete time functions. So one more problem. Evaluate the summation n from minus infinite to infinite del of n minus 1 sine 2n. Okay. So what is the result? These two product, that is del of n minus 1 dot sine 2n. This two product is valid, that is non-zero value when del of n minus 1. The sketch for del of n minus 1 at n equal to 1, the magnitude of the signal is 1. Exactly at n equal to 1 only, this product is valid. So at n equal to 1, this particular term would become 1. So the result is sine of 2 dot 1. Okay, sine of 2 dot 1. The result is sine 2. Either the impulse function available in the form of summation or in the form of integration, you have to apply this logic only. Check at what value of t or what value of n your del function would become 1. Then replace the remaining terms wherever the small n is there or wherever the small t is there, replace with the same value. It's optional only. You can concentrate the previous topic, but later students should not suffer. In case if the questions come for the examinations, you are ready to solve. Okay. So I think we spent more than 15 hours for first half of unit 1. Okay. I will just see the introduction to systems. Because unit 1 is introduction to signals and systems. So signals part we have completed. Introduction to systems. A system is a physical device. A system is a physical device. We can say a amplifier is an example for a system which accept some input signal and it amplifies the magnitude of the signal and give us output. Okay. Or a low pass filter is a system which accept some input signal and what is the function of low pass filter? So depending on the cutoff frequency of the low pass filter, it will allows up to that particular cutoff frequency in the output and it filter out the remaining signals. So like that, a system is a physical device. Okay, it's a physical device which accept some kind of input. For continuous time system, x of t. For discrete time system, x of n. Discrete time signal. Then the system process on this signal based on the characteristics of the system. Based on the characteristics of the system. Then it will give a output y of t equal to transfer function of x of t, or y of n equal to transfer function of x of n. What it represent the transfer function? System will do some process on the signals. Amplifier amplifies the magnitude of the signal. Okay, there the transfer function represents how much the amplitude is boosting. In terms of we are measuring the performance of the amplifier in terms of gain. Gain equal to output by input. Okay, like that, many physical systems are existing. The system accept a continuous time system accept continuous time signal. It process on the signal based on the characteristics of the signal system. It transform your input x of t equal to transfer function of x of t. Some other signals, that is output. In generally signals and system, we called the output of the system is response. Response of the system. How the system is response for a particular input. That is your y of t. Okay. So I'll write down the definition here. A system is defined as a physical device. Okay. That generates generate a response or output. Remember this word response. Find the response of the system, meaning find the y of t or y of n. The response or output. Response of the system or output signal for a given input signal. Okay. For a given input signal. So this is a definition for a system. So in our subject, we are not going to concentrate a particular system or the real time system, just the basics of the system and what are the classifications, a different type of system existing. Okay. Signals, we studied different types of classifications of signals. Similarly, so what are the types of systems present? Classifications of systems. So definitions of each and every systems and problems in each and every system. That is, some expressions will be given to you. You have to identify whether the given system is a linear system or non-linear system, or causal, non-causal, etc. Okay. How we identify energy signal, power signal, periodic signal, aperiodic signal based on some condition. So in systems topic also, we have to identify what type of system it is. First, static systems and dynamic system. Static system and dynamic system. Second one, linear and non-linear system. Linear and non-linear systems. And then causal and non-causal systems. Signals already we studied. causal and non-causal systems. Next category, time invariant and time variant system. Time invariant and time variant system. Okay. And fifth one, static dynamic, linear, non-linear, causal, non-causal, time invariant and time variant system. Next one is stable and unstable system. Stable and unstable system. Okay. So these are the major classifications. So apart from this continuous time system, discrete time system, and lumped parameters and distributed parameter systems. But anyway, we are going to concentrate on these five systems here. Definitions for each and every systems, and how to check whether the given system is a static system or dynamic or any one of these categories. What system is missing? Just 1 minute. Invertible and non-invertible. Invertible and non-invertible. So these are the total possible classifications of systems. So we shall continue the same system topic in the next class. Then we will solve the definition as well as problems for each system.